Okay, so it looks very complex, but it turns out that when you do this for a manipulator, okay, think of a robotic arm, maybe the 2 degree of freedom arm we talked about some time back. The equations always have this kind of form. Okay, so this will invariably give you this for a manipulator, always, which is good. We want to know the structure because once we know the structure of the equations, we can build very powerful control methods to ensure that we can work with those dynamics. So what are these terms? M of Q is known as the mass matrix. It'll have terms like mass, inertia, but the best part is that it's only a function of Q or the position. It's not a function of Q dot, which is the velocity. That's kind of important, actually. Then we have C, Q, Q dot. Oh, I forgot a Q dot here. This is the Coriolis. In this case, it will be Coriolis acceleration. So Coriolis acceleration typically has some velocity squared term. Also, sometimes dissipation shows up here, but then it's not nonlinear. It's not. There's a q dot, as you can see, that makes it squared. Q is position, q dot is velocity, so it's a function of q and q dot. It'll also have the mass matrix, but the inertia will not show up here. It'll also be a function of the length of the manipulator. Then we have this gravity term, g of q. So this is gravitational acceleration. So it's not simply mg, but because it's a two-link manipulator or three-link manipulator, that lengths and different masses will show up. So it's not very trivial. It'll have some cosines and sines and so on, depending on the configuration. And then tau is the external torque. External torque. So when we talked about this in the context of unactuated system, so let's say that the torque is 0, we typically wrote this as, so we took this equation and we wrote it as AQ double dot equals B, where A is MQ Q double dot and B is tau minus CQ Q dot times Q dot minus G of Q. Okay, so because we didn't have to worry about torque, we just did that. And then if you remember, I did this simulations of a two-link pendulum. It's basically uncontrolled, just started to flip in crazy ways, the chaos part of the two-link pendulum, and that's what it is. So that's how a pendulum will behave when there is torque is 0. But now what we want to do is we want to consciously use the torque. This is something we have control over. We have motors which can spread the torque, and we want this torque to basically make the manipulator follow certain, do certain things for us. Okay, now there are two classes of problems we are interested in. Okay, this is let's say an industrial manipulator which is trying to do something useful. So there are two objectives of control. Number one is what is known as a set point control. Okay. What that means is, let's say that there's a pendulum and it is hanging down. our goal is to apply a torque such that it springs up. So it springs up. So it goes upright. Let's call that theta equals 0. So this is basically the set point. We don't care how the pendulum will go from upward to downward position. We only care about one thing, which is at some time t, maybe 5 seconds down the line, 10 seconds down the line, it should be upright. So that's a set point control problem. We're only interested in the end point. The other type of problem, which is, so this is more like, uh, this one is uh, not so much in say a manufacturing plant where you're trying to go to a set point because you care about the trajectory shouldn't collide with objects, right? It's usually for demonstrations. If you want to show a pendulum in class or in the lab or do an experiment, that's what you do. But the other problem, which I think is more important and is used for uh, industrial applications, is called a trajectory tracking control. So an example would be if you have a two-link manipulator, and then you made the manipulator track a circle, track a curve, then that would be a trajectory tracking problem. Now, you might say, we've done this before, we've done trajectory tracking, but here's the caveat. When we did the trajectory tracking, we really did not do the tracking. What we did was we just set the position of the angles based on the inverse kinematics. We really did not consider the dynamics of the manipulator. So for example, if this is in the vertical plane, then gravity is going to affect your ability to draw the circle. So you just can't do set the positions because it's not going to do what you wanted because it has to work against the mass, inertia, gravity, and so on. So we will actually look at trajectories. Well, trajectory generation was a precursor to this because these trajectories, now for some things like circle, we know the trajectory should be as follows, as shown there. But for something like, say, we specify a point A, point B, we would like to get it to go from point A to point B in a smooth fashion without any jerk or without any velocity disc and so on. So that's why we did trajectory generation, which will generate the trajectory for the robot. So here's one. Another one could be that you might, and this is more what you'll see in industry, which is as a manipulator, it has to, let's say it starts over here. And then it might have to, so let's put an arm on it. Okay, let me just change it a little bit. So let's say that this is the manipulator, and then it has an arm, so sorry, a gripper, and then we want it to pick an object and put it somewhere else here. So move the object from there to there, and then it has to basically follow this path. So we come up with this path, we know this point, we know this point. So we can generate a smooth trajectory and then make it follow. Now, following that is non-trivial because, as I said, there's gravity fighting you, there's mass inertia. So what we'll do is we'll see how to work with gravity and Coriolis force and all these things which I presented earlier and make the manipulator move smoothly without, by following the trajectory, but without deviating from the trajectory and working with the mass inertia and so on. So